Okay, thank you very much. So like last time, as many of you are more in C-star algebras, I'm going to be giving a bit of background, and I will hopefully talk about recent results as well. But of course, getting the main idea of the framework is essential to get done first. In free probability, as I mentioned last time, there are these analogs of entropy, right? So classical entropy of a probability distribution with some density is like so. Right? If this mu is given by a density with a spectral vague measure, then you define its entropy in this way. Now, in the free probabilistic setting, when you have more than one variable, there's not such an easy way to write down entropy. But what Voiculescu did, Voiculescu, asked what would be the analog of this H, or analogs of H, for multivariate non-commutative loss. Now, I think since everyone here was here on Tuesday, maybe you still remember a bit what non-commutative laws are, right? It's this description of the joint moments of several non-commutative random variables, right? And so Voiculescu is trying to come up with an analog of this entropy, and you can't write it on an integral formula, but what you can do is, I guess, use the idea of, hopefully I spell this right, Boltzmann, right? And this is, coming from physics and especially statistical mechanics, that entropy, the entropy of some state, entropy of some macroscopic state, is like the log of the number of microstates that have that macroscopic state. And so Voiculescu interpreted this or applied this framework in an interesting way. So the macroscopic state is going to be the non-commutative law, right? So that's some non-commutative law mu, right? Which, I'll recall, right? This is a mapping from the polynomial algebra to C. That's, it's in fact a tracial state. And you might assume some bound as well. And then the microstates here will correspond to n by n matrix approximations.
I always, if I may just interject, I always think this is somehow overly complicated approach to entropy. Seems to me that entropy is just where you take it for granted that something has exponential growth, and the entropy is just the time constant. I mean, of course, that's what you're saying, but I somehow the word exponential is part of the language, whereas no one ever uses the word logarithm. It's just somehow a question of how established it is, in the general language on that. Okay, forget about it.
Yeah. So there, I mean, it is true that it's fine to think about this from the viewpoint of exponential, and I can write down that viewpoint as I'm going.
The thing has no mathematical content. It's just a question of. Well, I seem to be getting on to linguistics quite often.
Okay. Anyway, so I will comment on that later. Yeah. Okay. So what do we mean by matrix approximations? Well, in statistical mechanics, in various forms of entropy, right, there's always you're always taking some sort of limits, and you consider better and better approximations, and there's also limits based on n. So here we're going to consider. So again, let me mention here sigma dr, the space of non-commutative laws of D tuples. And then, as I mentioned also, there's a weak star topology here. And so then when we talk about matrix approximations, what would that mean? Well, let's say consider some open neighborhood, right? So let's say we're trying to approximate a specific law move, right? So consider some open neighborhood that contains mu, and then we can say, and here I think I'm going to use a lowercase n because otherwise I'll forget. So for this open neighborhood, we consider the set of matrix tuples. So let's say, I'll just write superscript n, xn in self-adjoint matrices to the D, such that the non-commutative probability distribution of x with a non-commutative law is in this neighborhood. Right, so this is again the non-commutative law of the matrix Xn with respect to the normalized trace on the matrix algebra. Right, so these will be our matrix approximations. And then in Wojciechowski's framework, it was you would consider the log of the volume of this thing, and then take some limits. So let me write this down.
How do you calculate the approximation? Are you saying that now?
Yes, by computing the volume of that set with the Lebesgue measure. Yeah.
Well, that sounds more easily said than done.
Well, right. So I mean, this is a definition, not a computation. I mean, so you consider the log. There's a certain normalization. Okay, so this here is just the normalization. I'm not going to explain it now because I'm going to talk about a different version that doesn't use Lebesgue measure anyway. Okay, but there's some normalization, and you take the lim sup as n goes to infinity of this, and then you take the infimum over the neighborhood's tau. Right, and so the idea here is basically that the volume of the space of microstates is approximately this, like some normalizing constant exponential of this. Yeah, so this. I'm sorry, my board work here was not very good, but you define the entropy of the law, which is denoted by the Greek letter chi. Chi of mu is this expression. And so this is saying that the volume of the space of matrix approximation should be approximately exponential of n squared times this entropy.
Well, how come entropy is something you define rather than calculate?
Well, you also have to calculate it, but there needs to be a definition first. Otherwise, what are you calculating?
Okay, I thought the entropy was a basic quantity.
Well, like I said, you can't write down something like integral of rho log rho because there is no density. Yeah, this non-commutative law is not a measure; it's a state on this C-star algebra.
Yeah.
And so you can't express it in density. You don't have anything to get your hands on to write down a formula for entropy. So you have to do more work to even define what you're talking about. Yeah. Okay.
But then for instance, people have an entropy. It's one way of measuring it. Maybe there's more than one way of measuring it. But Okay, so there's the idea of definition, but you just look at their native language and what is the relative, you draw their relative word frequency on log graph paper. And they get a straight line. And that's the entropy. The slope is the entropy.
Yeah.
That's probably good, probably pretty good for deciding whether someone actually wrote something. Well,
Yeah, right. But this is an entropy in a different context, right? Where you
Yeah.
don't, it's not like so first of all, it's not the discrete Shannon entropy, but then also it's not even the continuous differential entropy, right? It's an adaptation of that for this free probabilistic setting. And this also has heuristics from random matrix theory. But again, I don't want to go into that because what I want to talk about today is applications to von Neumann algebras. So yeah, free group von Neumann algebra specifically. So maybe first I should mention, yeah. So if you take x1, or let me say, I guess mu, right? Mu, the distribution of I say S1 through SD, which are freely independent semicirculars. Right, this is like I mentioned before, an analog of Gaussians in free probability. The spectral distribution is a semicircular shape from -2 to 2, and they're freely independent. And so this is like the most canonical example, and you can consider the von Neumann algebra generated by these things, and that will just be this reduced free product of the von Neumann algebra of the individual ones, which would just be an L infinity space. And so this will be isomorphic to the von Neumann algebra of the free group on D generates. Right, and so this free probability theory has given us a lot of information about the von Neumann algebra of free group. Yeah, okay. And in case you're wondering about this, why is this the same as this? Well, if you take a commutative von Neumann algebra, right, if you're taking L infinity of the interval from -2 to 2 as a measure space, that's equivalent to L infinity of the circle. And L infinity of the circle would give you Haar unitaries. And Haar unitaries would be like, an element with infinite order in a group von Neumann algebra. That would be a Haar unitary, right? And if you take D freely independent Haar unitaries, that gives you free group. I mean, you can also, of course, you can say freely independent Haar unitaries and get this as well. Yep. So, right. Yeah, and the free entropy of this distribution of the semicirculars, maybe I'll write sigma here. The distribution of the semicirculars has the free entropy just equal to, that's right. I think it's just equal to D. And therefore, and in particular, right, this is this is finite. So here's a result of Voiculescu. So suppose Voiculescu. Suppose that so suppose that you have x1 through xd, which are coming from M self-adjoint. So let, I guess here you have a tracial von Neumann algebra. Von Neumann algebra with tracial state. And let's assume that M is generated by them. Then, if the free entropy of the distribution of the x's is bigger than minus infinity. Yeah, so this entropy, like the differential entropy in probability distributions, it can take positive or negative values, right? So for instance, if you rescale your measure, then this will add something to the entropy. So you can actually achieve any real value, right? And so the condition that tells you that it has a large entropy qualitatively is that it's bigger than minus infinity. Okay, so if this is true, then you can deduce various things about the M. So then M has
Going to be smaller than minus infinity? No, but I don't understand like the opposite, like what, like.
it could be equal to minus infinity.
Well, equal to minus, so it's just, so if you wrote not equal to minus infinity, so it's just, you're basically asking for it to be finite. Or,
Yes. Yes.
I was just.
No, I'm not saying there's anything less than minus infinity.
Well, it doesn't have to be negative. Is the entropy, in this setting, is the entropy always negative?
It can take any real value.
What about plus infinity?
No, it can't take plus infinity. So if you have a finite, you have finitely many variables here, because so it is going to be so here. Okay, I'm going to abuse notation and write the entropy of the tuple itself. It's like less than, okay, I don't remember, but it's like less than or equal to some constant plus a constant times the L2 norm of x squared. So it can't be arbitrary. So if you have a certain x, then it has a certain L2 norm, and the entropy can't be any bigger than that. But depending on what x is, it could be arbitrary. For values of some value of x, it can be arbitrarily large. It can be it can take any real value. Okay, so then this is just this condition saying that it's not trivial, right? That it has some amount of entropy. So if this is true, then you have consequences for the von Neumann algebra. It does not have any Cartons of algebra, right? And also M does not have property gamma. Now, if you were von Neumann algebraist, then I would write this down, and you would say, "Aha! I know what those things are, and I care about those things." But I don't know. Do you guys know about what is Cartons of algebra of von Neumann algebras?
Yep.
Yes. Okay.
So
Property gamma.
What's the question? Well, sure. Well, that's Maria von Neumann, right?
Well, I'm sure that you know it. I'm asking everyone in the
Not
room.
only I, but once I was talking with Yuri Manning.
Yeah. But does anyone in the audience, everyone in the audience, do you know what property gamma is? Okay.
But if I do, like, if I'm told that it has no Cartons of algebra and has no property gamma, I'm unexcited. That means I'm not gonna care about this algebra because I can't handle it. I don't know what to do if I don't have a
You can't handle it, right? I mean, this is why Voiculescu is here to study free group von Neumann algebra, because you cannot handle free group von Neumann algebra, right? So the free group von Neumann algebra is it's hard to decompose into any of these things, right? So Cartons of algebra means basically, okay, so Cartons of algebra means an abelian subalgebra whose normalizer generates the whole thing, right? And so basically having a Cartons of algebra here, let me write this down. This means that, this arises somehow from, well, I don't know if I would say explicitly a group measure space construction, because maybe it's not a group, but some sort of thing like this. Yeah. Okay. Right. So maybe it'll say something like group measure space construction.
If the entropy is equal to minus infinity, Can you conclude that there must be a Cartman production?
No. So this is definitely not equivalent.
Go ahead and go out.
Right, okay. And then property gamma means that it has sort of approximate, that it has some non-trivial approximate center.
Yeah, but in terms of knowing the history, I would like to mention that Yuri Mannion said that when he was a student, he read the Murray Van Neumann paper.
Okay. Okay, cool. Yeah, so free group von Neumann algebras are kind of hard to decompose in this way, right? And that's the reason they can be very mysterious. But by using this entropy and quantities like this, we can actually get some kind of idea about their properties.
As far as we know, maybe all of those are in one control. Right? It's not, that hasn't been solved yet.
Sure, yeah. And in fact, I mean, this was one of the motivations for coming up with something like this, because one of Wojciechowski's ideas, is maybe by looking at your space of matrix approximations and somehow assigning a dimension to it, you could detect whether free group algebras for different number of generators are isomorphic or not. Now, this hasn't been done, meaning this problem is still open. And I don't really know if this is the right approach to solve it, but it certainly has given us a lot of information about the properties of these free group von Neumann algebras.
This is not obviously very interesting.
I mean, so this free entropy itself is definitely not an invariant of the von Neumann algebra. There is a free entropy dimension, and that's something which, as far as we know, could be an invariant, but also there doesn't seem to be any clear way to prove that it's an invariant for the von Neumann algebra.
If you take the specific generators of the free group of Neumann algebra, is it known exactly what the is, or is it
Well, yeah. If you take your semicircular generators, we know what that is exactly, right? So there's a whole, I mean, this is not what I was going to talk about in this talk, but there's a whole theory about transforming measures by some smooth functions and how the entropy changes in that case, right? And so that can give us a handle on what the entropy is, what we can, how to compute it. But what I want to talk about today is another version of this entropy where you actually do get something which is a von Neumann algebra invariant. And it doesn't distinguish between the different free group von Neumann algebras, because actually it will be plus infinity for all of this. But it is very well adapted to deducing a lot of these properties. Right, so let me mention here, so Kenley Jung wrote many papers about free entropy dimension. And there's a certain one where he defines a strongly one-bounded von Neumann algebra. And you might ask me why it is called strongly one-bounded. It doesn't matter. It's like, I mean, the answer to that, why it is called that, is technical, and I think the approach that I'm explaining today explains these properties. It doesn't explain the name, but you shouldn't care why it's called that. It doesn't matter. Okay, and so strongly one-bounded, this defines a certain property of, so he defined this in terms of, well, there's several ways that you can define it. One way is in terms of the free entropy of Gaussian perturbation of your x's, but another way is defined in terms of covering numbers of these microstate spaces. And so, and Jung showed that being strongly one-bounded is a von Neumann algebra invariant, meaning that you can compute it for one set of generators and another set of generators, and it always will give the same answer. Yeah, so this here, it defines a von Neumann algebra invariant. I'll write W star algebra for short, because it's equivalent to von Neumann algebra. And so then Jung-Hayes in 2018 And this was, I forgot when this was, but it was like 5 to 10 years earlier than this. And anyway, so Hayes defined some H, some quantity, which is like a version of free entropy, but it's using these covering numbers. So this calls this one bounded entropy, which again is a terrible name because you see this name and you think, oh, well, it must be less than or equal to 1 because it's one bounded, but that's not what it means. Okay, it's not less than or equal to 1. It's just some quantity, right? So H of x1 through xt, and this thing here, this thing is an invariant of von Neumann algebra, and technically also the trace, because yeah, if you have an infinite direct sum, then you have several choices of traces, and this can actually change the value. But so von Neumann, it's an invariant of the von Neumann algebra with its specified trace, and H being less than plus infinity is equivalent to saying that the von Neumann algebra is strongly one-bounded in the sense of Jung, basically. And so, being this is somehow like repackaging stuff from here, but in perhaps a more streamlined way. And now you can reason about this invariant here, right? And so, and the H, I'll get to the definition soon.
Won't define it, but yeah, different definitions or
Well, so I think so. Jung didn't explicitly write the definition of the H, right? So he defined this notion of being strongly one-bounded, and in the proof introduced such a quantity like this. And then Hayes explicitly wrote the definition of this quantity and proved other properties of it, you know, additional properties that had more applications. So let me give you a sense of what this H is. So unlike the entropy chi, right, which is, you know, either minus infinity or it's bigger than minus infinity. So here, so chi of x being non-trivial, bigger than minus infinity, implies that this entropy H is plus infinity. Yeah, so this is something which, yeah. And so then I should also say, well, maybe an obvious remark is that, well, if your von Neumann algebra is not Kahn-embeddable, then you don't have any matrix approximations. You know, if n is large, or if your neighborhood is small enough, then there will be no matrix approximations, right? So not Kahn-embeddable, then there will be no matrix approximations, and so then this will be minus infinity, and this will be also minus infinity, because yeah, you have no matrix approximation. So if you take the log of 0, you get minus infinity. Okay. Right, and this H, by the way, though, this H is, you know, it's either greater than or equal to 0, or it's equal to minus infinity. And the H is minus infinity if and only if you're not Kahn-embeddable, right? You have no things like this.
And some of those will have a cardinal subalgebra, some of them not.
Yeah, so I'll get to that Cartan subalgebra in a moment. First, though, I wanted to say, well, what about, you know, is so it's actually open. Does there exist some X with the H being finite and positive? So this would be kind of interesting because positivity of H implies that it has a lot of similar properties like the free group von Neumann algebra, like that it doesn't have Cartan subalgebra and so forth. But H being less than infinity would also mean that it isn't a free product. So let me talk about some properties and applications of it. I'm not going to get, I will give the definition eventually, but I wanted to give motivation first.
So the third board is to be something to the other.
Yeah, there is a third board, but you can only see two of them at once. I eventually have to erase them all anyway.
So
Okay. So, some problem.
your mind has a broad scope and a narrow scope.
Yeah, so anyway, more generally, Hayes defined H of n in the presence of M for n, which is a von Neumann subalgebra of M, which again has a given trace. So there's this notion here. And what does this mean? So the idea of this is that it looks at matrix approximations. So it looks at the amount of matrix approximations of n, which have some extension to matrix approximations of m.
What does a matrix approximation mean, given that it's not, the whole thing is not approximately finite dimensional?
Right, so this is approximations in non-commutative law using these microstate spaces.
Okay, you think we talked about that before.
Exactly. And I will make this more precise, but I did want to sketch properties first. This is just the intuitive picture.
I don't press the law in terms of some corresponding generators, corresponding elements of matrix.
Yeah.
Uh-huh.
So okay.
It looks a lot like it's reminiscent of embedding.
Exactly. Yeah. Right. So Kahn embedding is similar to saying, it's equivalent to saying that any non-commutative law can be approximated by non-commutative laws from tuples of matrices. Yeah. Okay. So about the properties of this. So one nice property is monotonicity. So if you have n1 inside n2 inside M, then you have this inequality. I guess I should also mention that the H of M that I was discussing before is equivalent to H of M colon M. Yeah, because I mean, if you have matrix approximations of M, they extend to itself, right? There's no extension you have to do. Okay. So then there's another monotonicity property. Yeah, if n is contained inside M1 inside of M2, then H of n with respect to M1 is greater than or equal to H of n with respect to M2. And the reason is, if you have to extend your matrix approximations to a bigger thing, then that's harder. So then that means that you look at fewer things. So you have this inequality. Okay. So let's see, what else do I want? I should look at my notes so that I write everything correctly. Oh, come on. Yeah, this is very good. A very important property here. Okay, so if n1 and n2 are inside M, and the intersection of N1 and N2 is diffuse, meaning it doesn't have any minimal projections, then you have subadditivity. So this here is the von Neumann algebra generated by N1 and N2 together. This is less than or equal to this entropy plus this entropy. Okay. Another one.
This is, here's a very naive comment, but the second line reminds me of the fact that within the algebras, one is contained in the other, and the commutant of the other is contained in the commutant of the first. But that maybe not, maybe that's one. So it may end up with some, well, there are some, it's an interesting systematic reversals of order.
Well, I'll talk about this. I'll talk about the proof of those properties in more detail later.
But
I'm not gonna.
I bet it had nothing to do with commutant.
Yeah, not exactly, but not it. This doesn't. I mean, I think there is some similarity, right? It's like you know how inclusions work with adding additional conditions. But anyway, where is that? Yeah. So yes, normalizers. Yeah. So this is now another great property. So if M is inside M, let's assume M is diffuse. And then if you have, so then the normalizer of N, and I know I used N already, but let me just write the norm for normalizer. So the normalizer of N, we'll consider unitaries in M such that U and U star equals N. Right, and so then the fact is that the Neumann algebra of the normalizer of N inside M, entropy of this inside M is the same. So if you add in things which normalize it, it doesn't change the entropy. Right, and if you think about well, Cartan-Sub algebras, it means the normalizer generates the whole thing, right? So this kind of makes sense why this could be useful. And in fact, you know, the most interesting results in Hayes' paper in 2018 were actually for generalizations of the normalizer. Right, so this actually works for various weak normalizers. So, for instance, if you replace this condition of equality with just saying that this intersect N is diffuse in here, this statement is still true. But all of these normalizers are sort of contained in this master object, which is called the singular subspace or anti-coarse subspace. I'm not going to go into that, but I just want to mention here, you know, some of these applications with normalizers, you read the statement and you're like, oh, well, we can prove that in a different way, so it's fine, right? But really, like, the power of this comes from, you know, or, you know, the results here that cannot be proved in another way come from understanding that this works for extremely general version of normalizers. Okay. So another property. So property / example. So if M1 and M2 are coembeddable, then they're free products. Has this entropy which is infinite. Okay, and another property or example, if M is amenable, then H of M is 0. Okay, so we'll see in a moment why this is, but let me, I guess, sketch this briefly, right? Is that here what we're going to do, we're going to look at these microstate spaces, and we're actually going to consider that we're going to kind of quotient out by unitary conjugation, right? So if two matrix approximations are conjugate by a single unitary, then we'll basically consider them to be the same. And if you're amenable, then any two embeddings into some von Neumann algebra, let's say with trivial center of 2, 1 factor, will have to be approximately unitarily conjugate. And then based on this, you can also deduce something approximate for the matrix approximations. If you're amenable, then basically all your different matrix approximations are approximately unitarily conjugate with better and better approximation as n goes to infinity. And so then that will mean that whatever, however you're measuring the size of this microstate space, if you quotient out by unitary conjugation, it's basically trivial. So then amenable things will have a 0 here, right? And of course, it won't be minus infinity because these are con-embeddable. So yeah, so this is 0. So,
Some measure of how well you can approximate by matrices.
yeah, in the sense of, yeah, it's a measure of like how many matrix approximations there are in a sense.
Could the converse be true that if you have H equals to 0, then it is more than equals to begin with?
Well, this converse is not true in general, but actually this is a good thing to mention here.
Before you reach the whole board, just have to propose another analogy related to this order reversing. If you have a bivariant function, or anything to anything, then it's sometimes it's covariant in the first variable and contravariant in the second one.
Yeah, sure. It's similar to that. Okay, so let me address this question of amenability, and now I think I will use the other board because I don't want to erase this stuff yet. So as you might have, so you might have heard of the Peterson-Thom conjecture. Peterson-Thom conjecture has to do with if you take amenable subalgebras in a free group von Neumann algebra, then it will be contained in a unique maximal amenable subalgebra. Okay, so okay, but let me first of all write this statement. So this is now a theorem. So if n is this inside a free group von Neumann algebra, and n is non-amenable, then H of n is strictly positive. So the statement that you were saying is not true in general, but we now know that it's true for subalgebras inside a free group von Neumann algebra. And this is a non-trivial statement. So where does this come from? So this is a combination of two results, basically. Well, certainly it could be infinite. We don't even know if it's possible for H to be finite, right? We don't have any examples. Yeah. So we don't, it doesn't, I'm not asserting anything if it's finite or infinite, just that it's not.
Negative values are out of the question.
Yeah, negative values for this are out of the question. Except 9 is infinite.
Like H of n not equal to 0, right?
Yeah, sure. And it's also not equal to minus infinity because it's con-embedded. Okay. Yeah, so this was a paper, random matrix approach to the Peterson-Thom conjecture, and this was like another statement in that paper, which is shown to be implied by the theorem that if you take independent Gaussian random matrices, right? And let's say x1 to xd and y1 to yd, then the operator norm of some so maybe I should say some polynomial of x1 tensor 1 up to xd tensor 1 and 1 tensor y. Right, so the operator norm here in the tensor product of this. Now, I mean, as you probably know, for a finite dimensional C-star algebra, and in general for a nuclear C-star algebra, there's unique tensor products. Right, so the C-star tensor products here, this, right, and these are random matrices. So they're random and also depend on n. So right here n. This converges as n goes to infinity to the norm of, I'll just abbreviate here this to x tensor 1 and 1 tensor y, where you're looking now in the von Neumann algebra of X, which is this free group von Neumann algebra, min tensor product itself. All right, so here this is, X is this free semicircular family.
This reminds me to some extent of something like in a long paper of Holworth and Hogrup and Thorbjorn.
Exactly, right? So this is like Hogrup and Thorbjornson looking at the operator norms of things, except now you have to do it with a tensor product of the two matrices and not just one tuple of matrices. And so then this theorem in turn has been proved. So at least there were two different proofs announced to it, and at least one of them is correct. And so Belinsky and Capitan here, and Bordenov and Collins, right, that they showed that this statement is true, and then Hayes actually earlier showed that this statement implies this statement.
Well, this must be quite early Hayes, because my recollection is that for a while he's been working on the C-star algebra. Maybe I'm
No.
okay.
I mean, Ben Hayes has done a bunch of things in dynamics as well, but I don't think he's done C-star algebra specifically.
No.
Yeah. So anyway, this is group C-star. Like we proved lots of things about group von Neumann algebras.
Oh.
Group, I don't know so much about C-star algebra. Okay, so right, so we have that result. I think I should wrap up the first half, but if you'll allow me a couple more minutes, because I know we started late a couple minutes, wanted to give you some examples of like how you apply the properties listed here. Sorry. Okay. So first of all, let me revisit the previous statement that I said about a free group von Neumann algebra does not have a Cartan-Stov algebra. Okay. In fact, I'll prove the more general statement here. So this is now I don't know, proposition. If M has a Cartan-Stov algebra, then H of M is less than or equal to 0. So here, i.e., it is 0 or minus infinity. Minus infinity if it's not quantum bound. Okay, as usual. So how does this work? So Yeah, so let's say let A be the Cartan subalgebra. Okay, so then H of M, or H of M in the presence of itself. Well, M is generated, so by definition of Cartan subalgebra, it's generated by the normalizer of A. And so then this would be the same as this. And then this would be less than or equal to H of A. And this thing here would be equal to 0 since the abelian A, the commutative A, is amenable. Yep. So I use the normalizer property here, and then I use just the monotonicity properties. Yeah, and looking at this, yes, if you have free products of con-embeddable things here, then this shows it doesn't have Cartan subalgebra. Hello. Okay, let me do one more. I think I can erase.
You also put it together with, so I think, so you had a statement that if we're living inside of a free group algebra, and then non-amenability would imply greater than 0.
Yeah.
Is there a conclusion that I can make? If I'm
Yeah, sure. So here, so you could say here that the normalizer of an amenable thing inside the free group von Neumann algebra has to still be amenable. And I believe that may have been proved already in a different way, right? But so one example would be, if A is a subset of LFD and it's amenable, then the normalizer, right? And also, all these weird generalized normalizers, this thing will also be amenable. Yeah, okay. So that's a very good observation. And then let me go back and do one more, which is using this property here. Right, so now here's another such proposition, right? Right, so if, in particular, if N1 and N2 are inside M, N1 intersect N2 diffuse, and N1 and N2 are amenable, then that would imply that H of N1 join N2 in M is less than or equal to 0, right? So this will be less than or equal to H of N1 in M plus H of N2 in M, which will be less than or equal to 0 because N1 and N2 are amenable. Yep, and so in particular, right, you take your free product, and then it's impossible to generate this free product by taking two amenable things which intersect diffusely. Yeah, and if you were to, iterate these operations, you can put these together in various ways. Okay, so okay. I think I should pause here for the break. Continue after this.